Welcome back, folks. We're looking at another theorem. This is probably the smallest of the theorems that we'll look at, but it ends up being pretty relevant in a lot of things we do. And it's called the maximum power transfer theorem. We want to make sure that we're getting the most power we can to the load, whatever that may be. So this is kind of an ideal time to talk about it because it's related. The answer to that question is how do we get the most power to the load? It's related to the Thevenin equivalent, the Norton equivalent, things like that. And we can think of those circuits in their equivalent form to do some of this analysis. So in your heads, I want you to think about stereo speakers. We want to get the most power to the speaker so that you go deaf as fast as possible. Not really. You should wear your protection and all of that stuff. I'll stop being a dad. You want to get the most performance out of the stereo that you buy. So if you look at the back of a stereo, or if you look at the back of a speaker, you're going to find a resistance value labeled. So you'll see 8 values is a pretty typical 8 ohms. I'm sorry, 8 ohms is a pretty typical value. You can find 4 ohms and 2 ohms nowadays, and that's all related to the maximum power transfer theorem. When we're transmitting power, we want to make sure we get the most power possible to the load. So we want to, if we have a factory at the end of a long distribution line, we want to make sure we get most of the power, the most power we can to that factory, so that it can be consumed at the point of service. I think those are a little more intuitive, but I also want you to think of data transmission. Since this is a computer engineering focused class, think about data transmission. How do I get a signal through a data cable reliably? Well, I want to get the most amount of power to the receiver. So how do I ensure that I get the most amount of power from the transmitter through a transmission cable, Cat 5, Cat 6, whatever you want, to the receiver? And that's going to be related to a lot of things, really, but part of it is the maximum power transfer theorem. Okay, there's a ton more examples, so I don't want you to get stuck on just those 3 examples. But let's start by looking at, let me move some stuff around here so that I can bring this up. Okay, so here are those 3 examples, and the answer, the question that we're trying to answer is what value of the load maximizes the power dissipated by the load. Okay, so RL is the resistance of the load, and P sub RL is the power dissipated by that load. Okay, so I usually open this up to questions in the class, and I say, okay, what value of RL do you think is going to maximize power transfer? And I usually get one of 2 answers really quickly. Somebody will say 0 ohms, and I'll go, not quite. 0 ohms is a short, and if I have a short up here in the corner where the load is drawn, then there's going to be no voltage across it, right? And we've got to remember that the power dissipated by the load, and we're going to use the functional notation, right? So this isn't a multiplication. I'm saying this is the power of the dissipated by the load as a function of the resistance of the load. Well, we can just say that that's the voltage across the load times the current through the load. Okay, so if it's a short and there's no voltage across it, then it doesn't matter how much current's flowing because we're not doing any work to move that charge, and power is work over time, right? So if we're not doing any work to move that charge, we're not dissipating any power. So we're certainly not maximizing power. Okay, so then somebody usually goes to the other extreme and says, well, if it's not 0 ohms, it must be infinite ohms. It must be an open. And I go, similar reasoning to why that's not the right answer again, because if this is an open, there's no current flowing, right? With no current flowing, it doesn't matter how much voltage is there. It's all potential energy, and none of it is causing current to flow. So there's no work being done. There's no energy being dissipated. If there's no energy being dissipated, power 0. So it's not 0 and it's not infinity. So it's not a short and it's not an open. So it's got to be somewhere in the middle. And we've got to figure out where in the middle is, right? Because what's infinity divided by 2? We don't know. So it turns out there's a very specific value for which we will maximize power. In order to do that, I'm going to take this this function here. Oh, I broke off my finger. We're going to take this function over here and develop it a little further, because if we want to maximize a function, I want you to think back to your calculus classes. How are we going to find the maximum value of a function? So hopefully you've already screamed it at the screen. We'll get to that. If not, you should be thinking about that. Go back to your calc prereqs. How do we find the maximum value? Okay, in order to do it, we need the function. So we want to maximize the power dissipated by the load, and the domain of this function is the resistance of the load. Okay, so let's start it off. So we've got this Thevenin equivalent. Maybe that's our stereo, maybe that's our power distribution system, or the transmitter network in a network card. But we can boil it down to a Thevenin equivalent, and that's why we handle maximum power transfer theorem here. Okay, so if I want to find the voltage across the load and I want to find the current through the load, then we can do a little bit of analysis. And look at this circuit. It's something that we know and love. It's the voltage divider, right? So let's start out down here by saying the voltage across the load is whatever the Thevenin voltage is. And we want to know the voltage across the load, and the Thevenin resistance is in series with the load resistance. Okay? Voltage divider. We know it, we love it, and it's kind of in a nice pre-canned form here. The circuit's drawn in a way that we're comfortable with. The formula applies directly. No tricky stuff there. All right. The current through the load over here, these are in series, and we know the voltage across both of them, right? So we're going to take the voltage across both of them, which is V Thevenin, and we're going to divide by R Thevenin plus RL. Okay, that's a voltage over a resistance, and that's going to give us a current. This is a voltage, this is a resistance over a resistance, which is going to be unitless multiplied by voltage, and that's going to give us volts. So think about those units. Stop and think about those units. Okay, so if I have these two formulas for the voltage across the load and the current through the load, then we do some substitution. So I'm going to take this formula here, right, which is just the power across the load as a function of the load resistance, and we can stick these together. Now, how quickly do I want to stick these together? V Thevenin. We'll go slow. I'll be good. Don't skip steps. I'm tempted to, but for you, I'll go slow. Okay. V Thevenin over R Thevenin plus RL. Okay. And that's just the voltage times the current. That's simple. All right, we can combine some things. We have two V Thevenins in the numerator, right? So we can say this is V Thevenin squared, and we'll have RL left all there by its lonesome. Okay, and then in the denominator, look, this is R Thevenin plus RL and R Thevenin plus RL. So we can say R Thevenin plus RL quantity squared. Okay, so getting a little more compact, but we haven't done anything too crazy, I hope. A little bit of algebra, that's all. So that's in its reduced form. Now, we want to find where this function is at its maximum. Maximum value. So that's what we're looking for. Find maximum value. And we want the corresponding value of RL. Okay? So we want to know where along the domain is the function at its maximum. In order to do that, we got to go back to calculus, and we have to think about the derivative. Okay, so where's the slope of this function? 0. Okay. So we're taking the derivative of the power dissipated by RL as a function of RL with respect to RL. Okay, so this is you know, a nice derivative. I think most folks in their first week of Calc 1 should be able to do that derivative in their heads. And I'm totally joking. I'm so joking. I plugged it in MATLAB. I really did. Okay. You're going to go find the derivative. I'm going to give it to you. Okay. But the concept is there that we're looking for where the slope is 0. Okay. And we find that derivative as v Thevenin squared. That's a constant if we're taking the derivative with respect to RL. The numerator ends up being R Thevenin minus RL. All of that is over R Thevenin plus RL. And now the denominator is cubed. Okay. Yeah, I use the big calculator for that one. Okay. We want to know where that's 0, because that's going to tell us the maximum point. All right. If this is going to be 0, then the numerator has to be 0. And we can kind of throw out the denominator, which is rather nice. V Thevenin, okay, times R Thevenin minus RL equals 0. So that's getting simpler. We can get a little simpler by dividing both sides by V Thevenin squared, which is really just going to be a constant. Okay, so that drops out. 0 over V Thevenin, it might as well not be there. And we end up with the much simpler form of R Thevenin minus RL equals 0. All right, now we feel like we're dealing with stuff that we can certainly do in our head. R Thevenin, add RL to both sides. And you're going to get R Thevenin is equal to RL. So when R Thevenin is equal to RL, can you remember that equation? I think you can. We have maximized power transfer to the load from the Thevenin equivalent supply. Okay, so let's do this. This is good numerically, and that's the payoff. Okay, I marked it in blue there. That's the payoff. You got to find the Thevenin equivalent. You got to make the load resistance match the Thevenin resistance, and you know you've maximized power transfer. It's not indicating that you've made it the most efficient as possible. That's just not true. Efficiency is something different. If you want to maximize efficiency, there's other formulas that you got to dig into, and there's other implications to trying to maximize efficiency. There's usually some other constraint put on it. But we're going to maximize the power transfer. Let's do this with numbers, because I know y'all love to see examples with numbers. Okay, so let's take a Thevenin equivalent. So let me draw this quick for you down here. Okay, we have a Thevenin equivalent, and we're going to connect it to a load. Okay, RL. And for this, I made that 2 ohms. This is 10 volts, and we're interested in the voltage across the load and the current through the load. And if I know those two values, then we can go calculate the power dissipated by the load. Okay, so I plotted this, and I plotted this using, I did it in MATLAB, and I used the formulas that we had above. I just plugged in values. I said the voltage across the load is equal to 10 volts over RL plus 2 plus RL. Okay, voltage divider for that one. Is this behind my head? I'm not sure. I don't have my preview up. The current through RL is 10 volts over RL plus 2. Okay, so where does this multiplied by this reach its maximum value? It better be at 2 ohms. That's the somewhere in between. It's not 0, it's not infinite. I'm saying it's 2 ohms. And what's going to come out of that, let me grab it for my clipboard here. Not sure if I'm ruining, it was on the wrong screen. Okay. If we plot those, since it's a function, we can plot them, right? Look at that pretty graph. I'll scooch over here. Oop, 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 oop. My contrast got messed up. There we go. We plot them. Okay, so the voltage across the load. When it's 0, right, when RL was 0, and that's what we have along the horizontal here, the domain of the function, we said that the voltage was going to be 0 across it, and that's what we see with the yellow plot. It starts at 0, and then since it's a voltage divider, we can never go above our source voltage over here, so this looks like it's asymptotically approaching 10, and it is. If we took it out to infinity, it would approach 10. Okay, the current, we said, is going to be 0 when we have infinite resistance. And if we look at this light blue line down here, it looks like it's asymptotically approaching 0 as RL approaches infinity. And it is. If we took it out to infinity, we'd see that it approaches 0. Where does it start? It starts at 5, which is kind of interesting, right? Because if this is 0, I have 10 volts over 2 ohms. Right? You can see that here in this equation as well. And it's going to start at 5, and then it heads towards 0 as I crank up the resistance. Multiplying those two things together, we get this kind of pink looking line here, and at 2 ohms we reach the maximum point. Okay, and the slope of the function at that point, tangential to that function at that point, is going to be 0. So that's when the derivative is 0. Okay, hopefully that's coming back to you from your calc classes. Okay, there's a numerical example for you. It's not 0, it's not infinite, it's somewhere in the middle. What is in the middle? In this instance, in the middle means that it matches the Thevenin resistance. Okay, I'm going to do 2 quick examples. I'll do a small one of finding the maximum power for a bigger circuit, and then we'll talk about the limitations of maximum power in the second one. So we've got 2 more videos on maximum power transfer, and then we move on to something else fun we can do with Thevenin and Norton's. Okay, stay tuned and good luck.